Hi, we are now going to learn about the internal structure of the atom. The modern atomic theory began with Dalton. Dalton proposed that atoms were these tiny solid spheres that could not be broken. They were unbreakable, indivisible. Now, if something is unbreakable, then you don't have to worry about the internal structure, right? You don't have to worry about what is going on inside because it can't be broken. But in 1897, J.J. Thomson discovered electrons. These were the first subatomic particles. He found out that atoms are throwing out electrons from inside. So what does that tell you? It says that atoms have electrons inside them. There are subatomic particles that are inside the atom. Well, if there are subatomic particles inside the atom, then the question comes up, how are these particles arranged inside the atom? So the structure of the atom becomes important. And Thomson started studying and thinking about this. Now, electrons are negatively charged, but Thomson knew that atoms were overall neutral, electrically neutral. So basically, the net charge on an atom is zero, and they are ejecting electrons. So inside, when these electrons are inside, these electrons will contribute to a negative charge. But overall charge has to be zero. So what does that mean? The atom must also have an equal amount of positive charge. Okay. Now, when you take an atom and you bombard it, electrons are popping out. So he tried a lot of experiments where he tried to bombard an atom, and every time he would found only the negatively charged electrons popping out. The positive charges never popped out. So he was not able to figure out the source of the positive charge. But he knew that overall net charge has to be zero, meant that there is positive charge, an equal amount of positive charge inside every atom, right? So what he did was to propose this plum pudding model because he didn't know the source of the positive charge. Okay, so he assumed that it was distributed overall over the entire atom. It was completely distributed. So if you bombard it, only the electrons pop out because this was actually part of the entire atom, right? So electrons were tiny particles embedded in the positive sphere, but the overall sphere had an equal amount of positive charge. So this was his plum pudding model. Why is it called plum pudding? Basically, the pudding is the positive sphere, and the plums are these electrons that are embedded in it. Okay, so that was the model that he had proposed. So this model was able to explain the overall neutrality of the atom. It was able to explain that there are these subatomic particles. It was also able to explain that if you bombard, the electrons pop out and not the positive charges, right? So all of this it was able to explain. But there were lots of other problems with this model. So for example, it could not explain known properties of atoms like valency. Okay, now chemists had studied atoms for much longer, and valency was a very well understood concept. But then this model was not able to explain that. It was not able to explain emission spectra of atoms. Atoms emit electromagnetic radiation. That was also very well studied, but then this model could not explain that at all. Nor was this model able to explain where this positive charge came from. Okay, so this model was not a very satisfactory model because it was not able to explain many things about the atoms. But this was the first model for the internal structure of the atom. So in that respect, this was a very important step in the direction. Of course, Thomson was also the person who first discovered the first subatomic particle, which is electrons. And that also turned out to be a very major discovery. So that's why we study Thomson's contribution, in particular, his model of the atom. We saw that in 1897, Thomson had discovered electrons, the first subatomic particles, and then he proposed the plum pudding model of the atom. He didn't know the nature of the positive charge inside the atom. So basically, he proposed that the atom was a big sphere with positive charge spread out all over, with the electrons embedded as tiny particles inside this big sphere. So that was his plum pudding model. In 1899, Rutherford discovered alpha particles by studying radioactive atoms. So he looked at radioactive atoms like radium and uranium, and he found that these emit alpha particles. These atoms emit alpha particles. He studied the nature of alpha particles, and he found out that these alpha particles were also very, very tiny compared to atoms. Just like Thomson had found out that electrons were very tiny compared to atoms, Rutherford found that alpha particles were very, very tiny when you compare it with an atom. But electrons were negatively charged. Rutherford found that alpha particles were positively charged. So alpha particles were these tiny positively charged particles. But not just that. When you compare it with the electron, alpha particles had a lot more mass. So because they were so small and they had so much mass, they were super dense positively charged particles. So alpha particles were super dense positively charged particles. And in 1906, Rutherford came up with a very interesting idea to study what is inside an atom. Basically, his idea was that he is going to bombard atoms with these highly dense alpha particles. So if these highly dense alpha particles go inside an atom, obviously because the electron is so light, right, it won't be able to stop it. So it is going to go through the atom, and that he felt will help him probe what is inside an atom. Basically, he wanted to understand what is the nature of the positive charge that is inside an atom. Okay, so he did a bunch of experiments, but these experiments turned out to be very inconclusive initially, because he found that some of the alpha particles were going through, some of them were getting scattered. He was not able to come to any conclusion. So he needed somebody else to help him out to do much more precise experiments. And so he roped in two other scientists, Geiger and Marsden. So together they came up with the Rutherford-Geiger-Marsden experiment. The experiment looks like this. This is the setup. Okay, but if you zoom into what is inside, the core experiment consists of a very thin gold foil with a detection screen around it, all around it. Okay, so basically a beam of alpha particles, a thin beam of alpha particles goes through like this, through a small hole, and goes and bombards this thin gold foil. Most of the alpha particles would go through like that, and then they'll be detected at the back. Some of them will get scattered, but the detection screen is all around, so the detection screen can track the deflection of the alpha particles. So this was the basic equipment that they had invented. Using this, they did a lot of experiments, and then let us look at what was the expected nature of the results and the actual results that they found by doing this experiment. Okay, so if you use Thomson's model said that there was a big sphere of distributed positive charge, right? So that was throughout the entire atom. The atom was a big sphere with distributed positive charge with electrons embedded inside it, right? Now the electrons have very little mass. On the other hand, the alpha particles are very, very dense. So the electron won't be able to stop it, right? And the positive charge of the atom is also distributed. So it also won't be able to stop it. So the expectation was the alpha particles will just simply go through, right? All the alpha particles will just go through. Basically, in Rutherford's words, what he was saying is the gold foil is like a thin sheet of paper, and the alpha particles are like very highly dense bullets. So if you shoot a bullet at a big piece of paper, what is going to happen? It will pass through. It will just make a hole and pass through. This is what he was expecting if Thomson's model was correct. But the actual results were quite interesting. What they found was most of the alpha particles did go straight through as expected, but then 0.14% of the alpha particles, they were deflected by a small angle. Okay, so some of the alpha particles were deflected by a small angle. And 1 in 8,000, which is 0.0125%, that is 1 in 8,000 of the alpha particles, they were deflected by more than 90 degrees, some of them even backwards. So it is like this, right? In Rutherford's words, he was saying, okay, imagine that I had this very thin sheet of paper and I shot a bullet at it. Most of the bullets go through, then suddenly one of the bullets bounces back at you. That's very surprising, right? You expect all of them to go through, then why did this bounce back? Well, if you expect a very fast moving, very highly dense alpha particle to bounce back like this, then that means to deflect a high speed alpha particle backwards, it must experience a huge force, right? Because it's coming very fast this way. If it has to bounce like that, something must have pushed it in that direction. Now, electrons can't do that because electrons are 7,350 times lighter than an alpha particle. So electrons can't deflect the alpha particles. So if electrons can't deflect, but then if you look at Thomson's model, the positive charge is distributed everywhere. So the density of the positive charge is also distributed. No, it's distributed everywhere. It's not very dense. So if it was distributed like this, then it will not be able to deflect. Now, if the negatively charged electron can't deflect and the positively charged, right, atom cannot deflect, but there is a deflection, so something must deflect, right? So this led Rutherford to suggest that the only possibility was that the entire positive charge, it should not be like what Thomson said, the entire positive charge must be concentrated at the center. It must be concentrated at the center. But not just that. Now this positive charge must also have a lot of mass, right? Only then it can deflect this backwards like this. So most of the atom's mass must also be sitting there. So two things. The entire positive charge must be sitting at the center, concentrated, not like what Thomson said, distributed across the atom, but concentrated at the center. And most of the atom's mass must also be sitting there. So Rutherford came up with the idea that atom must have a positively charged, highly dense nucleus, But if most of the mass is sitting here, right, and all the positive charge is sitting here, that means most of the atom must be empty space, because the electrons are tiny, right? So the electrons must be distributed around and most of the atom must be empty. It is not like what Thomson said at all. The atom has a nucleus. The nucleus has all the positive charge and has most of the atom's mass, right? So most of the mass is sitting here, and the electrons which have very little mass, they are distributed and most of the atom is empty. So that was the big conclusion from the Rutherford's alpha scattering experiments. So using his scattering experiments, you can see that very, very small number of the alpha particles are the ones that are getting scattered, but he studied this in great depth, right? He looked at different angles how they are getting scattered. So by looking at that, he was able to find out that the volume of this concentrated nucleus was really, really small. It was 10 to the power of minus 15 times the volume of the atom. That is, if you take the entire volume of the atom, this was 1 by 10 power 15 times that volume, right? So it was really tiny part of the whole atom was the nucleus. The nucleus was so much smaller than the atom. Now you of course know volume of a sphere is 4 by 3 pi r cube. So r is cube root of the volume, right? Proportional to cube root of the volume. So if you take cube root of this, you get 10 to the power of minus 5. So the radius of the nucleus is 10 power minus 5 times the radius of the atom. What is 10 power minus 5? Well, 10 power 5 is 1 lakh. So that means radius of the nucleus is 1 lakh times smaller than the radius of the atom, 100,000, right? 10 power 5 is 100,000, 1 lakh. So that means if the nucleus is this size, the nucleus radius is this size, the atom is 1 lakh times bigger. So I can't draw it here, it's huge, right? So the atom is mostly empty space. Okay, so the atom is made up of a very highly dense, concentrated positive charge, which he called the nucleus, Rutherford called the nucleus. Most of the atom is empty space and the electrons are somewhere on the boundary there. So this was a big departure from Thomson's model. So let us now look at Rutherford's model of an atom. Let us now look at Rutherford's model of the atom. Rutherford's alpha scattering experiments had already shown him that atoms are mostly made up of empty space. They are mostly empty. And they have a highly dense positive nucleus. And the nucleus is very, very small compared to the atom. So the atom is huge and the nucleus is really tiny, right? So basically, he knew that there was this very concentrated central portion which had all the positive charge and most of the mass, okay, very, very dense portion. So this was the nucleus. And the atom was so much bigger, that means the electron was actually quite far away from the nucleus. And most of the atom was empty. Now, of course, Rutherford knew that this is positive. If that was negative and it was at rest, then it is going to get attracted and it will fall into the nucleus, which obviously doesn't happen. So therefore, he proposed that the electron must be revolving around the nucleus in a circular orbit. And the radius of the electron orbit determines the size of the atom. So basically the size of the atom is determined by this radius of the circular orbit. The nucleus is very, very small. So its radius is much smaller than the radius of the orbit. The electron is the one that is roaming around at the boundary of the atom. So this was basically Rutherford's model. Now, if the electron is going around in a circular orbit, that means it must have a centripetal acceleration, which means there must be a centripetal force acting on it. What provides the centripetal force? Electric force, of course, right? Coulomb attraction, which is basically electric force. That provides the centripetal acceleration required for the electron to go around in a circular orbit. So this positive charge is pulling that electron, F. What is F? K Q1 Q2 by R square, right? Now I'm taking one electron, so that has a charge of minus E. So this overall the atom is neutral, so this nucleus must have a charge of plus E. So Q1 is E, Q2 is also E. I'm only talking about the magnitudes. So K into E square by R square. K is of course Coulomb's constant. So we know what is this Coulomb force, electric force acting on this electron. Okay, now that must be equal to mv square by r, centripetal force, right? So this must be equal to mv square by r, where m is the mass of the electron, v is the speed with which the electron is revolving around. So if I now look at this equation, I can cancel out one r, take the other r there and bring the mv square down. So I can then write r is k square by mv square, k square by mv square. Now half mv square is the kinetic energy, right? So this is 2 times the kinetic energy. So I can write R is K square by 2 times the kinetic energy, right? K square by 2 times the kinetic energy. Now K is Coulomb's constant, we know that. E is the electron charge, which also we know. So if I know the kinetic energy of the electron, I can use that to find the radius of the atom, which is quite a powerful thing that if you think about it, right? So Rutherford's model was a very, very interesting model. It gave quantitative ways to find out what the radius of the atom must be. Now, of course, you can say, I'm talking about here only one electron and therefore a charge here which is simply plus E. What if I had a bigger atom, right? So Rutherford basically said bigger atom means more positive charge, so more number of electrons revolving around. So something like this, you have a bigger nucleus and you have more number of electrons roaming around. So basically that was the core idea. Now remember that the atom is neutral. So the total positive charge on the nucleus must be equal to sum of the negative charges on all the electrons in the atom. So for example, if I had plus 3 here, plus 3 charge, that means I must have 3 electrons. I have 1 there, 1 here and 1 there. So that is the model that Rutherford proposed. Now Rutherford's model was very useful and interesting because it took care of several things. For example, charge neutrality of atoms was already included. You had a positively charged nucleus and you had negatively charged electrons, the total charge was 0, net charge was 0. So that was automatically included. But not just that, you had this huge atom, central nucleus, most of the mass was sitting at the central nucleus. So it was a very heavy, very tiny nucleus at the center, far away from the boundary, and all the electrons, light electrons, right, very little mass, they were roaming around at the boundary. So if you try to shake the atom, basically you bombard the atom, you give it energy, what will happen? Will it affect the center or will it affect the boundary? Obviously, it is going to affect the boundary. That is why only electrons are ejected, not the positive charges. That comes out beautifully from this model, right? So Rutherford's model was very brilliant. It allowed you to do a lot of predictions. But there were lots of other experimental facts which this model could not explain. Let us look at what they were. Let us now understand some of the problems with Rutherford's model. Rutherford's model proposes that the electron is revolving around the nucleus. This means the electron is accelerating. It has a centripetal acceleration. What is the problem with that? Well, in mechanics there is no problem, but Maxwell's electromagnetic theory, which was very, very well studied and had a lot of experimental evidence, it showed very clearly that any accelerating charged particle must necessarily radiate electromagnetic waves. And electron is a charged particle and it is accelerating, so it must radiate electromagnetic waves. Electromagnetic waves carry energy. And the electron is accelerating continuously, so it must be continuously emitting radiation, which means that the electron will keep on losing energy and it will spiral into the nucleus. As the electron starts moving around in this circular orbit, it will keep radiating out energy and it will start spiraling in and fall into the nucleus. But is that what happens? No, right? Atoms around us are quite stable. They don't collapse like this. That means this conclusion from Rutherford's model is clearly wrong. Not just this. If the electron basically spirals in like this, electron spiraling in will mean that the electromagnetic waves that are emitted must have continuously varying wavelengths. But in reality, experiments show that all atoms, when they emit radiation, the radiation is of discrete wavelengths. So that means this statement also turns out to be wrong. So that means these conclusions that we can arrive at from Rutherford's model unfortunately don't match reality. So this means Rutherford's atomic model can neither explain why atoms are stable, nor can it explain the observed discrete spectra of the atoms. Right? So there are clearly a lot of drawbacks from Rutherford's model. But despite all these drawbacks, Rutherford's atomic model was a huge step in our understanding of the internal structure of atoms.